To start this morning by introducing Johnny Brick from University of Virginia, who will talk about still other forest formulas in statistical physics.
Well, all I can say at this point is what a great meeting. I can't remember a meeting where I've seen so many connections between different areas, and in fact, so many talks which have preceded mine now are very useful in providing results which I need to talk about what I want to talk about. So I'm really happy to be here. I'm talking about forest root formulas, and it's going to combine aspects of Meyer expansions, polymer gases, and of course forests and trees, which we've seen all over the place this week, and also interpolation formulas. What I'm going to do is give two new interpolation formulas that can be used for Meyer expansions in hardcore gases, but they end up being relevant for other systems, as we'll see in a little bit. So let me start with an interpolation formula which I guess we can all agree with. Starting off slow at 9:30 in the morning. There's a little minus sign here, which there's a minus sign which is going to pop up from time to time throughout the talk, so that's where it comes from.
So you like to interpolate between 0 and infinity rather than between 0 and 1.
Yeah.
I mean, that'll be the case.
I used to do 0 to 1, but now I realize this is very natural to go from 0 to infinity.
So they're really different classes of formulas in those two cases? It's not just that one is a change of variables of the other?
Let me comment that in a few slides. I'll give you a better idea. Okay, all right, well, we need to go in a multivariable version of this. So let's consider a function which depends on three variables, t1, t2, and t12. And what we're thinking of here is that these are positions of the particles, and now they're half-line, all right? These are interpolation parameters, so we're going from 0 to infinity, so they're on the half-line. t12 then is the distance between t1 and t2. And then using partial derivative notation, we can first go out along the diagonal. See, we have chevron interpolation. We're going to first go along the diagonal, and then for each point on the diagonal, we're going to go either this direction or that direction. Anyway, so on the diagonal, we have the partial derivative with respect to first variable or the second variable, keeping t1 equals to t2, which means then that t1 minus t2 is 0. Now, we can take each of those two terms, the f1 term and the f2 term, and then we proceed to interpolate on the difference between t1 and t2. So if we take the t1 term, and we then separate the particles, there'll be two terms from, because there's two variables in f, and so you have to differentiate with respect to each variable. So you can differentiate either with respect to t2 or with respect to t1, 2, since when you move t2, this difference also changes. And then there's a corresponding term with 1 and 2 interchanged. Now what we can do is we can combine the terms involving f1 comma 2, and we've integrated.
So I'm sorry, so you could have integrated either term to infinity either horizontally or vertically, but you chose to integrate the f1 term one way and the f2
Yeah,
term
that's a good point. There are choices being made here. There's not a unique prescription. I just happened to pick this prescription because it leads to a nice formula. So the f1 comma 2 term, we combine this region with this region, and ends up being integrated over the entire plane. We can also, so that's right here. And so then there ends up being 3 terms in the formula. There's F12, which I think of as being 2 roots, F1, comma 1, 2, which means you have a root at 1, and then the 1, 2 gives a link, and then the corresponding term with 2 is a root.
But, I'm sorry, integrating over R, you have a function of 3 variables. So integrating over R2 plus means that the third variable is defined as absolute value T1 minus T2.
Yeah, that's right.
Whereas in the function itself, it's not forced that way.
That's right. Absolutely. And just as in the original thing, we integrate over a very specific hyper, or actually a line in the space, the 3-dimensional space. Now we're only ending up in a 2-dimensional subspace of the possible.
The original function f is defined on R3 plus.
Yes, right.
Can you go back and show us the formula?
Um,
I cannot find it.
Okay, well, let's see, do I have it? Well, I get the general case here.
Okay.
So, no, I didn't write down the formula, but basically,
Can you say again what F1 and F2 are? Sorry.
Partial derivatives.
The partial derivatives.
partial derivatives, that's right. I guess it's battery issues here, but.
And the comma and the no comma means what?
So some of the when I say 1, 2 without a comma, that means the variable T12.
You want to do is define.
So the function depends on 3.
That's
You can say that's engineer notation for partial derivatives.
Yeah.
Any engineer will be this way.
Uh-huh.
With a comma.
Oh, I wouldn't know.
A list of things separated by commas.
Okay.
All right, you're all set. So,
love this notation.
maybe I should go back to this. Anyway, so there, the formula is f of 0 is equal to this, except that the f12 term is integrated over the product of the half line with itself, plus the term with them reversed. So it's a sum over 4s.
But all 3 terms are integrated only over R2 plus, or some subset of R2 plus, and T12 is forced to be T1 minus T2 absolute value in the integrand?
That's correct, yeah.
Yeah, you do the derivatives and then you set T12 equal to T1 minus T2.
Yeah, so it's not a total derivative, it's a partial derivative. All these derivatives are partial derivatives. So the general formula, you can see the structure, what's going on. We're always integrating over a product of half lines. There's a sum over 4s and roots, which in the n equals 2 case was just three 4s. Okay, we're integrating. We have all these nasty minus signs. And you'll notice that the integration here with respect to the difference. So when I say that we're integrating over Rn plus, what I mean is that, for example, if it's T2 minus T1, it means T2 is greater than T1.
And this is really 2 integrals. There's a minus dtj and there's a plus dti there.
No, this is one variable. I just didn't introduce a new variable. Okay, this is one variable, which is T2 minus T1. Just like in the Chevron formula, if we integrate along this line here, we're integrating over the difference between 2 variables starting at 0.
It's a linear reparametrization.
Yeah, right.
But when you do it, I'm sorry, when you do it, or say, when you do that, that is a kind of total derivative, right? Because you're differentiating as T1 moves with T2 fixed. Both T1 and T12 are going to change, and both of those derivatives are included in there.
Yeah, they're both included in the formula. It's just that in any one term, there's only going to be one partial derivative.
Okay.
Get the bottom of that line.
Yeah.
Sorry, I'm sorry, that's not a derivative, I understand.
Okay, by the way, I should have mentioned that the naturally this function better go to 0 infinity, otherwise even the formula on the first slide isn't going to be true. Of course, you could have a generalization of this for, where you had a boundary value on the other end of the integration. But I'm not choosing to discuss that.
Is it true that integrating from minus infinity to 0, we never mess with signs?
Yes. Well, the thing is, ultimately there's going to be a sign which pops up from really makes a difference. It turns a probability measure into a non-probability measure, so it's not just notation. So I like to see where it came from. All right. All right. So here's what a general collection of forests looks like. There's some that are just have no links, but each of these tree graphs then has to have a root specified.
You go back once more to the graphical.
Oh, the chevron, this one, or no?
Well, what the graphical language means.
This one. Okay, so the circles are the roots, and the segments are the links, and the x's are the vertices of the tree graph. All right, well, to prove this thing, maybe I won't go in too much detail here, but just basically, you can prove this inductively. It's not too hard. You start with integrating on the diagonal, just as we did in proving the n equals 2 case. So then all these variables are the same. And then basically you take the the n minus 1 version of the formula to start at each point along the diagonal and then go off into r n minus 1 plus. And so then each root variable, each root derivative in that formula then gives two terms. A root will either sprout a link or it will be two independent terms, just as we found in proving the n equals 2 case. Anyway, that's probably something which is best left to private contemplation. What I'd like to do is see what this is formula good for. And oh yeah, there was a comment I wanted to make. There's a, implicit in this whole concept is that we have just two body interactions, if you will. T1, 2. In general, there'll be Tij, but there's what I would like to see is a formula involving 3 or n body interactions, and perhaps given that we've just learned about these 3 graph versions of the matrix tree theorem, maybe there is such a formula.
You're saying that you are going to tell us, or that you want to think about that in the future?
In the future, yeah. Or maybe that's for you fellows to think about.
That you should take. The point is that T12 is implicitly equal to minus T21.
Well, it's not. That's true, but that's not. A general function of n variables isn't necessarily represented. It is for, I guess, for 2 variables, for 3, T1 and T2. But in general, if you had 3 or more variables, then you might have some function of the 3 variables altogether.
But as it must be fully antisymmetric, it must be the determinant.
Well, I'm not necessarily thinking of antisymmetric functions.
Yes, absolute value there. But if you really think of these as particles on the half line,
Yeah.
then I believe if you know all of the pairwise distances, you can reconstruct the configuration completely up to translation. And so any multi-body interaction would actually be a function of these T.
Well, okay, that's true enough.
But in higher
With constraints.
But that doesn't necessarily mean that will be useful in generating formulas that are analogous to these forest root formulas. Anyway, that's just an idea. maybe for the future. All right, so what can we accomplish with these formulas? I want to apply them to hardcore gases. Basically what I'm saying is that these hardcore gases have to have two-body interactions. But as I said, general two-body interactions are problematic because of stability. You can't just interpolate interactions willy-nilly because you may end up spoiling some of the key properties of the interaction, like stability. So this particular interpolation may not do so well for a general two-body interaction. You may need to use the BK, Bridges-Kennedy, Abdus-Salam-Rivasot interpolations for the more general case. But I guess I forget whether it was version 1, 2, or 3, but we're looking at the hardcore gas, and then the exclusion between the particles obviates any problems with regard to stability. Oh, by the way, now there are numerous formulas in this book in '95 by Abdus-Salam and Rivasot, and one of those in particular is related to this interpolation formula I gave, but unfortunately the margin is too small to demonstrate it. But if you look at their theorem,
The margin's too small to write it.
So here's the page from that book. There's this condition that there's no interaction for levels differences at least 2, and that's kind of related to what's going on with this formula, as we'll see when I develop it further. But you have to work really hard to get. This is one of those things where you change variables, go from 0 to infinity to 0 to 1, but it's more than that. So anyway, this is really just for a little joke. So oh, by the way, perhaps this paper suffered from the fact that it was immediately following the paper of Witten in the book, so maybe it got overlooked.
Is this the trees, jungles, and forests?
All right, so let me look at the hardcore gas partition function, which we've seen many times already. We have an interaction, the hardcore interaction U, and I'm putting, at this point, a dummy variable in 0 with a view towards later interpolation. And here the xi are the spatial variables, and the xij is the difference. So we want to extend this function u into the interpolation regime. So we want to pick utx so that when all the t's are 0, you get the hardcore condition. Namely, the hardcore condition is supposed to be a product of 1 minus an indicator function. So the indicator function being a ball around the origin. So here's what I choose for the interpolated hardcore conditions. So we take 1 minus the indicator function, but then we interpolate it away when t gets bigger than 1. Now, you may say this is contrary to the idea of interpolation because
It's a set.
it's a step function, but okay, well, go with me. Actually, that's part of the reason why it's difficult to translate this formula into the AR formula. But okay, the derivative of theta function is a delta function, and we can work with that. Okay, so then I'm going to actually work with the density. So we take 1 over the partition function, and now since I'm referring to the interpolation formula, the arguments refer to the t variables, the interpolation parameters. F of t, I have to put in some conditions to keep these force f to go to 0 at infinity. So we have a bump function g, and which depend on some epsilon, and as epsilon goes to 0, the particles are allowed full reign to go out to infinity. One of them is then going to get stuck at 0, since that'll be the since we take a density, we have to have at least one particle to work with at the origin. All right, so we're going to apply the forest root formula, which I've reproduced here, to this f of 0, which is this product.
I'm sorry, so G is a smooth bump function as a function of variables x?
No, of t. See here, I'm basically suppressing the x variables. They're just going along for the ride at the moment.
Right, so in the G, there's also variables x that's going
No.
to the right? No. So how is it that G is constraining where the particles are?
It's constraining where they are in t space.
Or in T space?
This forest root formula, there was a condition there which said that the function had to go to 0 at infinity.
Oh, I see. So that you're using particle location to both mean location in x space and location.
Yeah, well, I'm trying to, eventually they're going to become one location, so
Okay.
it's moving in that direction. All right, so here's our function that I'm going to interpolate with the forest root formula. So it's really the integrand inside this integral over all these n positions of the particles in d dimensions. Okay, so what happens? We get an extra dimension, if you will. So instead of integrating over Rn or Rd, it's R plus times Rd. Now this, actually, in this case, I want to consider not, we're considering really two cases at once. Either the positions of these particles can be on a lattice, Zd, or on continuum, Rd. The lattice would give something like dimer models or various hardcore lattice problems. And if we were in Rd, it would be hard spheres, for example.
So can you go back a step? I'm confused about this interpolation parameter. Go back one more slide.
Mm-hmm.
U of t and x. You have a single global variable t? Or you have I don't understand where...
No, there's a t. These are the t's. I've just omitted the subscript. There's a single function, u, which is used for all the variables.
But how many t's are there?
There's one, you can think of it as an extra dimension for each particle.
For each particle. Okay, so there's a ti.
But there's only one hardcore potential, which is valid no matter which pair of particles you take.
But then I don't understand. U is the hardcore potential, right?
Yeah.
Or the cutoff hardcore potential. So is that t a global parameter? Or do you have one t for each particle?
Well, initially we have a hardcore potential where there's no interpolation parameter at all. It's just u, which I call u of 0.
All right.
And then that hardcore potential, then I extend into the interpolation regime by letting it depend on t.
Yeah, but I just don't understand how many t's are there?
It's the same as
one global, one for each particle, or one for each pair of particles?
as far as the function u, there's only one t because it only depends on.
Yeah, but in the formula.
In the whole formula here, there's going to be, as before, there's going to be a t for each I going from 1 to n.
Okay, so you have a t, and then
you have all the tij's as well.
okay, so in the interpolation, when I'm sorry, let me ask again. Up in the top formula, u is a function of a single xij, right?
I think that it's u of tij xij.
Yes,
where you
yes,
put
you-
the t equals to
Yeah,
one.
right. So this would be, I set it to 0, but this would be a tij.
I thought you said there's one t for each particle.
Can I have a
So
go?
it's
Yeah,
right,
as many
yes.
t's as many x's.
I would say it this way. Give every particle a t coordinate as well as the x coordinate that it started with. Right? The interpolation is to let the particles get far away from each other in t-space. So what you do is you extend your potential so that it's now a potential defined on x and t. The two-body potential is defined on a pair of xt variables as opposed to a pair of x variables. It's an extension.
Right, okay, so let me try again. You have
Actually, let me make a further explanation here. Traditionally, what we do is when we do a Meyer expansion, we multiply u by some interpolation parameter like tij. right? We multiply uij by some tij. Okay, I've chosen a slightly different way to interpolate u by doing a functional interpolation. I just define u as a function of a new parameter t and x,
Right,
and
I
vary that
understand,
parameter.
But I don't understand which t, so when you're working on particles ij, the x argument is xij, right? Which is actually shorthand for absolute of xi minus x.
Same for TI.
Right, and exactly the same. So for when you're working on particle ij, the relevant t is absolute ti minus tj.
No, there is a new t that is called Tij.
Well, as long as you do derivatives and at the end you make substitution, something
Right,
like
the
that.
point is the only t's that actually exist as independent variables,
Yeah.
are one for each particle.
Right, when you do where's the forest root formula? Here. The only integration variables are the t's. And okay, there's a shift in the origin for the t integration, but then all the variables tij are derived from those t's by tij equals
Right.
ti
And
minus
as Roman
tj.
says, you separately differentiate with respect to them, but then you evaluate at Tij equals absolute Ti minus Tj.
Yeah,
May I make another question which is different but will add confusion?
okay.
As long as you use only theta function, instead of adding a true extra dimension, you could have just added the easing spin. Because theta is just a switch.
Well, I don't know, maybe you're thinking about it a little bit different from the way there is an extra dimension, it's the t's.
But you're just partitioning your R to the n space into 2 to the n subspaces and actually just summing over subspaces,
Yeah.
not integrating. So,
Well,
the
okay.
spin was sufficient maybe.
Yeah, all right. Well, yeah, maybe there would, I mean, ultimately you can apply this forest root formula in other contexts. It doesn't have to be n particles on a line. It could be, instead of x sub I, it could be phi of x. It could be field variables as a function of, it could be field variables. That's maybe what you're thinking of.
No, well, I was thinking only on the auxiliary space.
Yeah.
But I
Okay.
don't want to mess.
All right. Yeah, I'm not sure. We'll have to talk about that later.
We'll have to ask the audience. It's not very common.
Could you go back to
Is that the one before?
just the slide the one that we're at?
Oh, okay. All right.
Yeah, that's
All right. So, all right. So, what happens when you apply the forest root formula? What happens is we have all these derivatives, and we differentiate a u. We get something which I call a v, which is the indicator function times the delta function. So, what this means is that for every link of a tree, you've got this constraint that the t must be equal to 1. The time difference must be equal to 1. So anyway, we get this, actually now we start with forests, but the two different trees in the forest end up getting very, very far apart and become independent, and the limit as epsilon goes to 0. And in the end, we just get this spread out probability measure, and we end up only looking at one tree when we work, for example, with the density as we've been doing. So the formula then is, so we got these minus ones, and then we've got the integral.
They should be inside the sum, right?
The minus 1?
Yes.
Or inside the sum.
Yes.
Oh, yeah, okay. That's the problem with cutting and pasting formulas. And then now we have a sum over trees rather than forests, and the integral is over r plus times s, which is either rn or zd, or zn or zd or rd. We've got these links, and then we still have the exclusion for the ij's which are not in the tree graph. So these trees basically are living now in an extra dimension, although it's only a half an extra dimension. So this is the type of structure you get. Now this, I'm talking about the lattice case where we start with ZD. And you can see why I was interested in having this step function interpolation. Since I want to have a stat mech interpolation of these graphs that I'm generating, well, you could have soft connections vertically, but since I'm starting with a hardcore gas in the horizontal direction, it makes sense to have hard connections in the vertical direction as well. So that explains the use of the step interpolation. So anyway, these upward links are the V's, where the particles are constrained to have a vertical displacement of 1. And the horizontal steps, they can also go, if you just take the simplest ball indicator function, the unit neighborhood in ZD, then we have 3 types of upward moves, either straight up, left, or right. We still have the interactions between these particles at the same level. In other words, there's hardcore conditions at the same level, but for different levels. Well, it wouldn't really be relevant anyway, but we don't have the U's between a particle here and a particle here, for example. Anyway, so this is what you would call a directed branch polymer. Directedness because all these t variables are on the half line, so you're always forced to go up and up and up. What we've got basically is this identity then between the density of the hardcore gas and a generating function for directed branch polymers in this d+1 dimensional space. And then all those minus signs have to be inserted. And actually, this makes this is an important distinction because the minus signs matter. Let's say you were interested in ZdBP of at a positive value of the generating function of the argument z, then that would correspond to a negative activity in the hardcore gas, which is an unphysical activity. That it means it's not a probability measure. But nevertheless, there is a lot of, actually that's where the interesting critical phenomena goes on in hardcore gas because of the alternating nature of the Meyer expansion. So what we see then is the critical phenomena that goes on at this at negative activity here is the same critical phenomena that we see in one more dimension for this directed branch polymer problem. And so as a result of that, you can make equations between critical exponents. This particular model, which I drew here, you can, it's a dimer type model. And in one dimension, you can exactly compute the pressure, and this is what it is. You see the square root singularity at the negative value, negative a quarter. And then then we have this exact equation. Then we have the computation of the directed branch polymer generating function by differentiating the pressure, and you can get the actually compute the just expanding this logarithm out, we can get these coefficients. And this also has the same inverse square root. Now, well, this you differentiate a square, you get an inverse square root singularity. And then you can do the asymptotics on these coefficients here, and you learn that there's the theta, which governs the asymptotics for the number of directed branch polymers of size n, is equal to a half. Other examples, you can play around with this. You can choose different balls around the origin, or you can go to the continuum, for example. You do have a directed branch polymers involving disks, which would look something like this. You can also go to the two-dimensional case and work with hard hexagons. And then the singularity there is known from the Baxter's solution, and from that you can determine the value of theta for a three-dimensional directed branch polymer problem. Related problems, okay, there's very similar results actually have been obtained for directed animals. This goes back to the 80s. Dar, I think, is the person who's most associated with, Dar and Semeta, most associated with these results. Bousquet-Malou, et cetera. They basically, as I understand it, you have you look at the dynamics of the hardcore gas, and then that ends up looking like directed animals. So directed animals would be like the directed polymers, except that there are loops allowed. And as you would expect, there actually is the critical exponents don't know whether you have loops or not. And so basically both problems then end up getting related to the hardcore gas in d dimensions. And those other problems which have come up recently, DeFrancesco and Gitter did these Lorentzian semi-random lattices, which we saw briefly in one of the other talks earlier in the week. These are also related to directed animals and also to the d=1 hardcore gas.
Can we say that for continuous models, directed animals and branched polymers are the same because loops at probability 0 in the back sets? If you have the spheres which touch one each other, well, closing a loop as the back measure 0 in this theta angle.
Well, but no, I don't think it would be measure 0. I mean, yeah, if you take a tree and force it to touch itself, that would be measure 0 in that one integration domain. But you could have additional disks that you would attach. And so you could certainly come up with, I think, a non-trivial directed animal version with disks.
Where the disks overlap to form the cycle rather than having to have their centers equal.
But these
Yeah.
cannot overlap. You have 0 if you overlap.
Well, you could.
Sorry, I interrupted you again on your line.
Yeah. Well, you could, all right, you could have this situation here, and then you could still define integration variables.
My point is that this one has a one dimension less in the back sense with respect to the partition function of the same number of variables for the polymers.
Yeah, but they're different terms, and it could easily be given appropriate weighting, so they have 0 relative weight. But anyway, that's for another talk. All right, now I want to move on to. I see I'm running a little short on time, but I did want to mention a two-dimensional version of this formula where we basically try to do the same steps, except that I don't want these, instead of these t variables, ti living on the half line, I want them to live in the plane, or the complex plane. So now instead of the t's, we have w's, which live in the complex plane. And the t's then are derived from the w's either by taking the norm square or the norm square of the difference. Now once again, we can think of these w's as being positions of particles in the plane rather than in the half line. The new formula then looks very similar to the old one, except the integration, we still have that nasty minus sign, and the integration is over the entire plane instead of over the half line. Once again, we can look at the case n equals 1. F of 0 is the integral of f prime. And just by going to polar coordinates, you get, actually reduces to the n equals 1 case of on the half line as the very first slide. So this basic identity is, we're going to jack this up to n dimensions, if you will. But it's much less trivial. You can't just give an inductive proof as we did in the half-line case. what we need to do is go and define differential forms. Really, in this case, okay, you could try to use fermions, but it's natural to use forms here because we have this spatial structure in the problem. We've got these W variables, so why not use DWs for your Grassmann variables instead of just introducing them from out of thin air. So anyway, so these are key formulas to define the right combination of W's and DW's to generate this forest root formulas. Now, if we have a function of all these variables, the TI's and the tau i's and the tau ij's, it'll be defined by its Taylor series using the usual rules for multiplication of differential forms. Now, one key aspect of this formalism is that if you have a loop of in the graph space, the ij space, all these two forms, wij, since they're really the difference, wi minus wj, there'll be if you have a loop, there's going to be a relation amongst all the difference variables in that loop, which means that the product of two forms will give you 0. And that ultimately is why when you introduce these anti-commuting variables or these differential forms, you are immediately led to formulas involving trees or forests. When you expand f of tau by means of its Taylor series, then you end up getting a bunch of forests where each link corresponds to one of these two forms, wi wedge wj, dwj. So then this forest root formula that I'm trying to derive here is in form language, it has a very simple way of writing. It's just the integral of f of tau equals f of 0. And where does this pi come from? Well, it's basically the change of variable. We have this 2 pi I in the denominator from the integration, but then we have a 2i from going to complex coordinates to spatial coordinates, and the net effect is a minus pi in the denominator. Okay, so if you try to go and do a inductive proof of this, I say, good luck. I don't think it's going to be going to happen, but you're welcome to try. There are a couple of different proofs of this formula. There's a cosmological proof using David Bridges' term, which involves supersymmetry arguments. But here in this conference, I think it's best to use a more earthly argument, which goes back to Bridges' Wright, 88, by working with Laplace transforms. So basically, any function t can be converted to the Laplace transform variables. And we have the dual variables to the t's and this inner product between the a's and the t's. Now, you could also do the same thing where, it was my choice to use w's for my fundamental variables of integration, but you could, for example, use p's. And then all of a sudden you're working in momentum space. And then these a's would be like Feynman parameters. Or you could use phi's. And then all of a sudden you're working in field space. So this forest root formula has other applications besides just working with hardcore gases, or at least other potential applications. Okay, by linearity then, if this function is represented as if it decays exponentially, it's represented as a linear combination of these exponentials. So all I need to do really is to prove the formula for exponentials, which is a lot easier. So there's a tiny bit of algebra that needs to be done here. A dot t is represented. It needs to be represented as a quadratic form rather than as an inner product of a with the t. So to accomplish this, you just define a quadratic form by negating the aij and then taking this combination of the a's. And really what's going on here is when you expand this out into its four terms, there'll be some terms like aij, dwi, dw bar I, and so those are properly put into the diagonal piece. So that's why we have these off-diagonal pieces combined with the diagonal piece.
So this is a Laplacian matrix with mass term.
Yeah. And the fact that x decays exponentially means that the aii are positive. Or the sum, yeah, aii is positive. Positive real part, anyway. All right, so then we have this nice cancellation of determinants. If I integrate e to the minus a dot t over Cn, first of all, you need to do this form calculation. A dot t becomes that. And here's the bosonic part, so to speak, and the fermionic part. And when you integrate out the fermions, basically, or really it's more like a change of variable in this notation, you can always get a determinant. And then, all right, I'll try to finish up quickly. The boson integration will give you an inverse determinant, and so then the product is 1. And so that establishes the forest root formula in the case of an exponential, and therefore by linearity you get it for a general function. So what have we learned? Actually, this connection with matrix tree theorem 1 is equal to this integral, which we just evaluated. And if you expand this out using the rules of differential forms, you get a sum over forest roots, as always. And then this integral here, as we know, gives the bosonic determinant gives you the inverse determinant. Put this on the other side, we get the determinant is the sum over forest root. So this is the forest, the matrix tree formula. So maybe it should be called the Kirchhoff-Witten theorem, because if we use the cosmological proof. All right, to get the, you have to go back to the A language to get the, so this is re-expressed in terms of the A's to get the traditional way of expressing the matrix tree formula. And as we've seen these by other people have talked about these Grassmann proofs of forest root of matrix tree. All right, so what can we do with this? Let me just quickly give you the branch polymer version. We've already seen the directed branch polymer. These t variables, the w's live in 2 more dimensions. So if we start with this hardcore gas and interpolate the hardcore potential like this, by again introducing this Tij, this then becomes in d plus 2 dimensions a nice symmetric ball of hard cores. We get the same issues of the trees decoupling, and in the end we get these tree graphs with hard disks, which I would call then the branch polymers in d plus 2 dimensions. So we start with the x variables, we add the w variables, which are in 2 dimensions, and so now we have the y's, which are the combination that live in our d plus 2. And so this branch polymer generating function looks like this. The links now, remember we differentiated u to get the links, so we differentiate this indicator function, you get the surface measure on the sphere. Critical exponents, we have can solve the problem in 0 dimension, the hardcore problem in 0 dimension, and in one dimension. And therefore, we can actually write down this generating function for branch polymers and learn the values of theta in 2 and 3 dimensions. All right, so anyway, this has been the additional identities, Kenyon Winker 07. And I didn't want to close without thanking my longtime friend and collaborator, which most of this stuff was done, David Bridges. Thank you very much. Sorry for going a bit over.
Thank you very much. So the audience already asked several questions, but David?
Well, I just wanted to say that I don't think it's a serious problem if you apply this formula to the case of attractive stable potentials, because there are always many ways to extend a stable potential into 1 or 2 extra dimensions so it remains stable. You can simply multiply the 2-body potential by another thing in 2 dimensions such that it's the Hadamard product of 2 matrices. If they're each individually positive definite, then the product of Hadamard product of the 2 is positive definite too.
Oh, okay. So if you do it in the right way, it'll, okay. Because I think I remember that was the issue with that big formula which I put from the Riviso book that was supposedly not working in that case. But
Just a quick question. You showed how the principal-minors matrix tree theorem is a special case of the second forest root formula, right?
Yeah.
If you know the principal-minors matrix tree theorem by some other proof, does that allow you to simplify the proof of the general forest root formula? Because you, after all, said that you only had to prove it for exponentials anyway.
Yeah, well, yeah, if you don't care about the difference between exponentials and general functions, then I guess my attitude, I guess, is that the basic concept is this fermion integration. And that's like calculus. That's part of the operating system. It really, or should be for everyone. And so then really the matrix tree theorem is trivial. I mean, it's just, okay, just write it out, and that's what it says. You get, there's no loops. So I wouldn't set that up as some grand theorem which you would use. It's just part of the operating system, and yeah, basically they're the same. They are equivalent in the case.
So you're saying that
you are right. I mean, the matrix tree theorem, since you have it for exponentials, you do get it for
right. Because there are lots of proofs of the matrix tree theorem, some of which are fairly elementary and don't use Grassmann algebra. But are you also
do the same?
But are you also saying that Abdeselam's Grassmann proof of the matrix tree theorem is more or less the same as your proof of the forest root formula?
Yeah, you just replace size by d5s. Slightly more special, this proof, but same structure.
Yeah, but still, I would emphasize that. I mean, I did it right here. It's just a 2-line proof or a 1-line proof. You just expand it out. There are no loops. So ultimately, when you look at things the right way, they become very simple. Yeah.
Yes, in combinatorics we have some often problem about the density of the gas on an infinite lattice. For example, which is equivalent to the directed animal in dimension d+1. So you show the Catalan, the dimension 2 is very easy with Catalan number. Then dimension 3, which means the hard hexagonal model of Baxter.
Yeah.
Then the generating function is again algebraic.
Yeah.
And this is not trivial. It's, you have to go through German identity and you need to Q, and then you get algebraic generating function. And we don't know how to explain this directly. And then the open problem, if you take the density on the infinite square lattice, then Baxter's solution does not work, and maybe it's still algebraic. I don't know. I asked the question to Deepak if it's algebraic in any dimension, and he feels maybe yes. So there is some. We are very concerned about this open question. In your framework, do you think you can say something about algebraicity of?
Well, it depends on the hardcore gas. I mean, I wouldn't have any. The problems are equivalent, so if there's any reason to believe the hardcore gas has an algebraic density, then or pressure, then But actually, what it did intrigue me to thinking about going the other way. You're saying that in any dimension, the dimer problem
No,
is.
the density, the number of
The
directed animals.
But the directed animals.
Dimer problem has no sense on an infinite lattice. As soon as you take the thermodynamical limit, then you have because it's this directed animal on the. Well, the 3D, let's take the directed animal. 3D directed animal, it's a genetic function. Is a directed animal on any dimension still algebraic?
Yeah,
Okay, maybe it's a good
All right.
discussion.
we may perhaps postpone this. There was still one last question. Okay. So then,
All right.
thanks to speaker again.